the last lecture we learnt how to solve the non-homogeneous system of equation A x equal to b, where A is in f m cross n and b is in f m. We found that there are several questions connected with this problem which we were still not able to arrive at. What we were able to do was that when b satisfied the consistency condition, we knew how to find the solutions. In other cases, when b did not, we did not even know how to proceed. In order to attend to such questions, we want to develop certain mathematical framework. The main mathematical framework in which we shall work is what is known as a vector space. In this lecture, we should look at what exactly a vector space means. While dealing with a non-homogeneous system A x equal to b, we have to encounter two column matrices, namely b which is in f m, which is given, and x which is in f n and which is to be found. The main fact is that we have to deal with such vectors or column matrices f m and f n. So, we shall now have a look at the structure of such column matrices. So, to look at this, let us look at a general k which is a positive integer. Let us look at any positive integer k and then look at f k, which is the set of all column matrices which have one column and k rows and with all the entries coming from f. Let us in particular take f equal to r, so that we look at the set of all one column k row real matrices, all the entries are real. Now, if we look at such matrices, let us take two such elements x and y in R k. X will be x 1, x 2 and x k, and y will be y 1, y 2 and y k, and remember these x's and y's, the x j and the y j are all real numbers. We are looking at R k. So, all the entries in the matrix are real numbers. Now, if you look at x 1, it is a real number, and y 1, it is a real number. We know how to add real numbers. So, we can get x 1 plus y 1, which is again a real number. Analogously, we can do this for every entry there. So, for each I 1 less than or equal to I less than or equal to k, x I plus y I is well defined, because x I is a real number, y I is a real number, and the sum of these two real numbers will again be a real number. Now, therefore, we have got these k new real numbers, namely x 1 plus y 1, x 2 plus y 2 and so on, x k plus y k. Now, we form a column matrix whose entries are these sums x 1 plus y 1, x 2 plus y 2 and so on, x k plus y k. Now, since this is a column matrix and it has k rows and one column and all the entries are real numbers, this is an element of R k. So, starting from two elements in R k, we have now generated a new element in R k using the addition operation which is in R, and therefore, we have a new addition in R k induced by the addition in R. So, hence addition which is plus in R induces an addition which also will denote by plus in R k as follows. If x and y are as above, x plus y is now defined as x 1 plus y 1 and x k plus y k. This is definition. It should be noted that the plus on the left hand side, this plus refers to addition in R k, which is being defined, and the plus on the right hand side and the RHS plus is addition in R, which is known. That is, the known addition in R induces an addition in R k. So, thus we are able to start with two elements in R k and define their addition, and the addition is in R k. So, thus we have an operation of addition on R k. So, the first major operation on R k we have is plus, which is induced by the plus in R, and this plus which has been induced we call as addition in R k. Let us look at some of the properties of this addition. So, we have the properties of addition which we denote by plus in R k. Let us look at three elements x 1 to x k, y 1 to y k, and z 1 to z k. Of course, one of the properties that we should always keep in mind, that when we add x and y, the result is always again in R k. So, the plus of two R k elements is again an R k element. So, let us note that as the property 0, that is x and y belong to R k implies x plus y belongs to R k. Now, let us take this property 1. We are taking three elements x, y, z in R k. Now, let us look at x plus y. We have seen that the sum of two elements in R k is again an R k. So, this x plus y is an element in R k. Any element in R k can be added with another element in R k. So, x plus y plus z is an element in R k, and what is this? X plus y is x 1 plus y 1, x k plus y k, and this is the definition of x plus y, and plus z, which is z 1 z k. Now, again on the right hand side we are adding two elements in R k. So, the usual addition definition given above says that this is equal to x 1 plus y 1 plus z 1, x 2 plus y 2 plus z 2, and so on, x k plus y k plus z k. Now, if you look at each entry, they are all additions of real numbers. I am adding x 1, y 1, z 1, these are real numbers, x 2, y 2, z 2, these are real numbers, and so on. And we know that in the real numbers bracketing can be done anywhere, that is, real number addition is associative, and therefore, we can write this as x 1 plus y 1 plus z 1 and so on, x k plus y k plus z k. This is because of associativity. This is called the associativity law of addition in R. The addition among real numbers follows the associative law. Now, this can be rewritten again as x 1 to x k plus y 1 plus z 1 etcetera y k plus z k. This is again by the definition of plus in R k. We have given above the definition. According to that definition, this sum will be equal to this. This is x plus, and what is appearing here by the definition of addition again is equal to y plus z again by the definition of addition in R k. So, therefore, what we have observed is plus on R k, the addition R k is associative. That is x plus y plus z is the same as x plus y plus z for every x, y, z in R k. So, first we have defined the notion of addition, then we have observed that this addition is such that whenever x and y are in R k, their sum is also in R k, and then the addition obeys the associative law. The next property we observe about addition is the following. Look at the vector or the matrix theta k 0 0 0 0. Now, the 0 on the right hand side is the real number 0. So, in R we have this real number 0. Now, we have formed a matrix, column matrix, all the entries are 0. Since 0 is a real number, this belongs to R k. This has the property that if we now add x to theta k, by our addition rule it will be x 1 plus 0, which is again x 1, x 2 plus 0, which is again x 2, and x k, and it will be the same as theta k plus x, because 0 plus x 1 is x 1, 0 plus x 2 is x 2, and this is true for every x in R k. So, the property that we observe is the 0 in the real numbers induces a 0 in the R k, in the set of column matrices. So, this is the conclusion we have, that is there exists a column matrix theta k in R k such that x plus theta k is equal to x is equal to theta k plus x for every x in R k. So, this is the next property we see of addition in R k. Again let us recall, addition is such that when x and y in R k, x plus y is also in R k, addition was associative. Now, we see that there is a vector analogous to the number 0 in R, there is a vector theta k in R k such that x plus theta k is equal to x for every x. So, this is the next important property of addition on R k. The next property that we observe is the following. Suppose we have a vector x in R k, say x is x 1, x 2, x k. Now, x 1 is a real number, and therefore, every real number has its negative. So, minus x 1 also belongs to R. X 2 is a real number, and therefore, minus x 2 also belongs to R, and so on. X k is a real number. So, minus x k also belongs to R. So, take a vector or a column matrix X in R k, look at each one of the entry, that being a real number, look at its negative. Since every real number has its negative, we can find all this minus x 1, minus x 2, minus x k. Now, we form a new vector or a new matrix k by 1 matrix, whose entries are now minus x 1, minus x 2 and minus x k. Since minus x 1, minus x 2, minus x k are all real numbers, this is again in R k. Therefore, from x we have constructed a new element in R k and we will denote this element by minus x. This is the definition. If x is x 1, x 2, x k, the corresponding minus x element in R k is defined as that matrix all of whose entries are negative of the corresponding entries in x. And then clearly now by the addition rule of R k elements, we see that x plus minus x is equal to theta k is equal to minus x plus x for every x in R k. So, what we see here is that the corresponding to the number 0, it induces a matrix 0 or the vector theta k or the element theta k in R k, and corresponding to the number minus x, we have a matrix minus x or the vector minus x or the column matrix minus x that has been defined, which behaves exactly like the 0. In the real numbers, we had a number plus its negative is 0. Now, we have an element of R k plus its negative is the 0 element of that space. So, this is the third important property. When we have these three properties together with the fact that x plus y belongs to R k for every x and y, we have what is known as the notion of a group. We say R k forms a group with the operation plus that we have defined. So, basically the real numbers form a group, the real numbers are such that addition is present, the addition of two real numbers is a real number, there is the 0 real number and every real number has a negative real number which is such that x plus minus x is 0. All these properties induce corresponding properties on R k, and therefore, the group structure of R induces the group structure on R k. Further, if we have x and y, we have x plus y is x 1 plus y 1, x k plus y k. Now, x 1 and y 1 are real numbers and x 1 plus y 1 is the real number addition, and real number addition can be done in any order, or in other words the real number addition is commutative, and so we can write this as y 1 plus x 1 y k plus x k because of commutativity of addition in R. But now by the laws of addition in R k, this is the same as y plus x. So, therefore, the commutativity of addition in R again induces the commutativity of addition in R k. So, we have x plus y is equal to y plus x for every x y in R k, or addition is commutative in R k. Now, we already seen R k forms a group with respect to addition, and if this particular addition is also commutative, we find that it is a commutative group. R k plus with respect to the addition is a commutative group. In general, for an arbitrary group, we will replace R k by an arbitrary set plus as a new rule of combining two elements. If this rule of combination, which is normally called as binary operation, obeys the properties that when you combine two elements from the set, the result is also there, and there is an element akin to 0, and for every element there is an element akin to the negative, then we call it a group. And if this rule of combination does not obey any order, then we call it commutative group. So, the first thing that we structure, that we observe about R k is that R k plus is a commutative group. They are also known as abelian group. Now, we can abstract this and generalize. In place of R k, we can take any set G. So, let V be any non-empty set. And in place of plus, we take some operation. So, let plus, we will also denote that plus. See, we are denoted by the same plus addition in R, we have used the same symbol plus for addition in R k. Now, we use the same symbol plus in an arbitrary set V for an arbitrary rule. Let plus be a rule of combining an x in V with a y in V to produce an element in V which we will denote by x plus y, which we denote by x plus y. It is only symbolic. The result outcome of this combination is x plus y, such that we have all the, we now demand all the rules that the plus obeyed in R and R k to be obeyed by this new rule of combination. What are these rules? We had the 0th rule, x and y belong to V, then the result of the combination must also be in V. We say V is closed with respect to plus, V is closed with respect to plus, this operation plus. Then we demanded associativity. So, x y z in V implies x plus y plus z must be equal to x plus y plus z. This is the associativity of plus. Then we wanted the existence of something akin to 0. So, we had 0 in the real numbers, theta k in R k. Now, for a V we shall call it a general theta V. There exists an element theta V in V such that what was the property required of 0, when it combines with anything, the result is what you combine, x plus theta V equal to x equal to theta V plus x for every x in V. That is the role played by 0 generalized now. The role played by the negative is going to be generalized now. What is the role of negative? For every real number x we had a negative real number, for every x in R k we had a negative x. Now, for every x in V we need a negative x which should also be in V. The negative of a real number was real, the negative of a R k element was again an R k element. Now, we want the negative of an x in V to be in V, such that what was the role of the negative? the element and the negative combine together to produce the 0. Now, the role of 0 is played by theta v. So, we need this. Then we also had the commutative law, that is x and y in V. Whether we combine x with V or y with x, we must get the same result. This is the commutativity of plus. So, whenever we have an arbitrary set V, we started with an arbitrary set V, and we have a rule of combining two elements in that set, and if that combination rule obeys these properties, namely V is closed with respect to this plus, that is the result of adding or combining two elements is again in that set, the set is self contained with respect to this operation, and this rule is associative, and there is an element akin to the 0 element in real numbers, and there is the negative of every element, and the rule of combining is commutative. Then we say V together with that operation plus is an abelian group. So, this is the abstraction or generalization of the ideas that we get from RK. We had first a structure in R. We get the RK by putting several copies of R. We put k copies of R. First element is R, second row entry is R, third row entry is R, the kth row entry is R. So, we put k copies of R to get RK, and whatever properties that R had, the RK carried over it. The same thing, addition properties were carried over, group structure was carried over, commutativity was carried over. Now, we have generalized all this and we get the notion of abelian group. Before we see examples, we will also look at another operation, the second major operation in RK. Second major operation in RK. The first major operation was addition. Now, we look at the second major operation in RK. What is this operation? Now, consider any element of RK. It is of the form x1, x2, xk. There are k entries, each entry is a real number. Now, take any real number alpha. We have x1 is a real number, alpha is a real numbers, and therefore, alpha x1, the product of the real number alpha and the real number x1 is well defined, and that is also a real number. Similarly, the product of alpha and the real number x2 is well defined, and that is a real number, and so on, and alpha xk is a real number. Therefore, starting with these real numbers x1, x2, xk, multiplying each one of them by the real number alpha, we got k new real numbers alpha x1, alpha x2 and alpha xk. We now form a new element in RK as follows. Take the first entry as alpha x1, second entry as alpha x2 and third kth entry as alpha xk. Since each one of these entries is the real numbers, this is RK. This is in RK. So, starting with the element x in RK, we started with an element x in RK, and then we took a real number alpha, we combined the real number alpha and the element x in RK. So, we are now combining a real number with an RK element. we have combined a real number alpha and an Rk element and produced an element in Rk. This process is what is called as scalar multiplication. So, we define this as alpha x, this is the definition. So, this is the rule of combining a real number alpha and an element x in Rk, and this rule is called scalar multiplication. That is, you are multiplying an element in Rk by a scalar alpha. So, what is scalar multiplication? So, scalar multiplication is a rule which combines an alpha in R with an x in Rk. What is the important property or properties of scalar multiplication? Once again, we will call it the zeroth property. When we combined alpha, a real number, and an element x in Rk, we got an element in Rk. Therefore, the rule combines alpha belongs to R, x belongs to Rk, implies alpha x belongs to Rk. The result is again in Rk. Now, it is easy to verify that if I take two real numbers alpha and beta and then multiply it, scalar multiply it with a, when I add alpha and beta I still get a scalar. Alpha is a real number, beta is a real number, so alpha plus beta is a real number. So, combine this new real number alpha plus beta with the element x in Rk. So, when you combine a real number, this is a real number, this is an element in Rk. When you combine, you must get an element in Rk. How does that look? The rule of combination is alpha plus beta into x1, every entry must be multiplied by that scalar. Now, alpha is a real number, beta is a real number, x1 is a real number, and real number multiplication distributes over addition. So, the first entry is alpha x1 plus beta x1, alpha xk plus beta xk, which is because of distributivity of plus over multiplication in R. Distributivity of multiplication over plus, let us put it that way. It is a more appropriate way of saying the multiplication distributes over addition. Now, this by definition of vector the addition in R1, it is alpha 1 x1, alpha 2 x2, alpha k, alpha xk plus beta x1, beta x2, etc. beta xk. But again by the rule of scalar multiplication, this is alpha x and that is beta x. So, the conclusion is this is the first property, alpha plus beta into x. This is true for every alpha beta in R and for every x in Rk. Similarly, if you take alpha any real number, beta any real number and multiply it with the element x in Rk. So, alpha and beta are real numbers, alpha times beta is a real number. So, the real number alpha beta is combined with the element in x in Rk, the result must again be in Rk. This is the same thing as first combine the real number x with beta, you get an element in R k, then combine the real number alpha with this element in R k, you obtain. And you have the real number 1. If you combine that real number 1 with the element in x k, what do we get? According to the law of combination, we must multiply every entry by alpha. Now, alpha is 1, so I will get 1 times x 1, but 1 times x 1 is x 1, 1 times x 2 is x 2, and so on. So, I get back the element x for every x in R k. Then finally, supposing I have an element in R k, I take another element in R k, now I can combine or add or plus 2 elements in R k, and that will be again an element in R k. So, I have an element in R k here, I can now combine an element in R k with a scalar. So, suppose I do this, and what do I get? I get what I would normally expect. Sorry, this should be alpha y. This is true for whatever alpha real number and x and y in R k. So, now we have two operations in R k. One operation is about addition, the other operation is about scalar multiplication, and if you look at this fourth operation, this is an operation which combines the addition operation and the scalar multiplication operation. So, this is the rule which relates or combines and makes these two interact, these two operations interact, the scalar multiplication and the addition operation, their interaction rule is provided by these. Otherwise, the first 3 properties or 4 properties 0, 1, 2, 3 that we wrote of scalar multiplication and the other properties of plus, they live independently, they do not involve a mixture. But now, this property involves both scalar multiplication and addition in R k. So, this is a very important rule, it combines the two basic operations that we have studied so far. When we generalize all this, we get the notion of a vectorized space. Generalize all these, we get the notion of a vector space. So, what is, we had R k, we have to replace this by an arbitrary non-empty set. Then on R k we had an addition that will have to be generalized to an operation plus on B. Then we had the rules for plus and they will have to be generalized for as rules for plus. Then we had scalar multiplication here. What is meant by scalar multiplication? So, multiply by R. Now, this has to be generalized. This R is replaced by what is known as a general field. F is a field, we will see more examples as when we deal with examples of vector spaces. This is the general form of the generalization. Field, the notion of a field is akin to the real numbers with both addition and multiplication, and take all those properties that addition and multiplication have in R and put it as an abstract form, we get the notion of a field, and therefore, this has to be generalized as multiplication of a V element with an F element. This is the generalized version of a scalar multiplication, and then we had the rules for scalar multiplication, and that has to be generalized for rules for scalar multiplication. When we do all these generalizations, we get the notion of an abstract vector space. So, we shall now give this formal definition of a vector space. So, let V be an arbitrary non-empty set. This is the set which plays the role of R k, and then let F be any field. This F plays the role of real numbers. So, the role of R k is played by this arbitrary set V, the role of R is played by the field F. Then we had two operations, addition and scalar multiplication. So, let plus be a rule of combining x y in V to get x plus y. What we get, the result will denote by x plus y. Such a thing is called binary operation, and then let dot, the scalar multiplication will denote by dot. After some time we will stop writing the dot also. Dot be a rule to combine an alpha in F with an x in V. So, this now the role of V, the V plays the role of R k, F plays the role of R. Addition in R k is now played by this operation or the rule of combining two elements in V, and multiplying as R k element by a real number R is now replaced by multiplying an element x in V by the field F, by the field element F. So, these are. Now, what are the rules? Such that, let us list the rules of addition first. We will now list them in continuous numbers. The first one was, when we add two R k elements, we got an R k element, that is R k was close with respect to plus. Analogously, when we combine two elements in x y, the resultant is also in x y. So, this is what is V is closed with respect to this rule plus. It is also said that plus is a binary operation on V. Then the plus on R k was associative, and that is what we are going to demand. X y z belongs to V implies x plus y plus z is equal to x plus y plus z, that is plus is associative on V. This is called the addition on V. The addition on V is associative. Next, we had the role of 0 in real numbers, theta k in R k. Now, we want the theta V. There exists an element theta V in V such that, what was the role of the theta V? When it combined with any element, it produced the same element. That is the rule of theta V. Then we had the notion of, for every element there must be the negative role, that is, for every x in V there must exist an element in V. Remember, the negative of a real number was real number, the negative of an element in R k was in R k. Now, the negative of an element in V, we want it to be in V, such that what makes it negative, when it combines with its, when an element combines with its negative, it produces the 0. The 0 is now the theta v, the role of 0 is played by theta v is equal to theta v is equal to minus x plus x, 0 minus x plus x. These are the properties of plus that we demanded. Now, we will list the properties of scalar multiplication. We had alpha belongs to f. Whenever in RK we had alpha was in R, the role of R is played by the field f, and then we took an element in RK, now we take an element in V, and there we formed the scalar multiplication. Now, we write alpha dot x. After some time we will stop writing the dot, we simply write alpha x, and this must be in V. When we scalar multiply an element in RK, we got an element in RK. So, when we field multiply an element in V, we must get an element in V. Then we had these properties alpha beta in f, x in V implies alpha plus beta into x is the same as alpha x plus beta x. This is the what we see here is the addition. There you see an addition symbol here. This addition refers to addition of alpha and beta. Alpha and beta are field elements. So, this is the addition in the field f. We see a addition on the right hand side. This is adding alpha x and beta x. Alpha x is an element in V, beta x is an element in V. So, the right hand side addition is plus in V. So, now the plus in f has been converted to a plus in V. So, this is a relation which combines the addition operation of the field with the addition operation of the V elements. Next, similarly, if alpha beta in f, x is in V, then alpha is a f element, beta is an f element, the product of two f elements is an f element. So, that can be combined with a V element. The result must be a V element. What is that? First, combine the f element beta with the V element x. The result is again a V element that can be combined with the f element, that is alpha of beta of x. And we had that important property which combines scalar multiplication and addition in V. So, we had alpha in f, x and y in V imply alpha x plus 1. Now, x is in V, y is in V, therefore, this is the addition in V. When we add two elements in V, we get an V element. This V element and this f element are combined, we will get a V element. What is that V element? First, combine the f element alpha with x, combine the f element alpha with y, you have two V elements, you add them. And finally, we had the 1 in the field, and if you scalar multiply an element in V, you must get x for every x in V. So, let us now go back. What are all the ingredients that we required? We required an arbitrary set V which played the role of RK. We required an arbitrary field which played the role of R. So, we had this V playing the role of RK, we have the F playing the role of R, then we have the operation of combining two elements in V which plays the role of addition in RK, then we have this rule of combining a scalar alpha in F with an element in V, this plays the role of scalar multiplication in RK, then this plays the role of the fact that addition of RK element with RK element is RK element. So, now we want addition of V element with A element is V. This plays the role of associative law of addition in RK. This plays the role of the 0 matrix in RK or the 0 column matrix in RK. This plays the role of the negative vector or negative matrix or negative column matrix in RK. This rule 5 plays the role of the fact that when you multiply an RK element with a scalar, you get an RK element. Now, we say multiply a V element with a scalar in F, we get a V element. This plays the role of multiplication and addition, scalar multiplication with respect to addition of scalars, and multiplication of scalars and scalar multiplications are expounded here, and addition of B elements and scalar multiplication, how they combine. This is again the role where we saw the two basic operations of scalar multiplication and addition, how they interact with each other. Then we have this 1 into x equal to x. When we have all this, then we say V is a vector space over the field F with respect to the addition operation plus and scalar multiplication operation dot. Should all the 4 things play an important role. First of all, the set V plays an important role, the field F, because these are the people who are being combined. The addition combines V elements, scalar multiplication combines F element with V, and the result is always going to be in V. So, these two are going to play important roles, the V and the F, and then without these two rules of addition and scalar multiplication, there is no structure. So, this addition and scalar multiplication play an important role. So, therefore, we have to say it is a vector space over the field F with respect to these operations plus and scalar multiplication. All the 4 play an important role in the structure of the vector space. So, all these, if for example, if we retain the same F, if we retain the same V, so we retain the same set V, we retain the same field F. Suppose we change the operation plus and still have the same properties, then we will have a vector space, but this will be different. This will still be a vector space over F, but it will be a vector space over F with the new operation. So, in a vector space there are 4 important ingredients. One is the set V, one is the field F, and the operation plus addition and the scalar multiplication operation dot. Together with all this, we get the notion of a vector space. We will just call the elements of a vector space are called vectors. We shall see in the next lecture a number of examples of vector spaces. Many of these examples we will encounter in some problem or the other in physics or engineering or in mathematics. We shall be looking at the example in the next class.